Hi guys. Okay, so we've made it to chapter 2, and tonight we're going to look at properties of polynomials, part 1. So we're looking at polynomial functions, and the first question is, what is a polynomial function? So a polynomial function, and if you look at this definition, it's really scary looking. F of x equals a sub n x to the n plus a sub n minus 1 times x to the n minus 1 plus dot 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 plus a sub 3 times x to the third plus a sub 2 times x squared plus a sub 1x plus a sub 0. That's really scary sounding. Really what it is a number times x to a power plus a number times x to the next lowest power plus a number times x to the next lowest power plus a number times x to the next lowest power until you run out of x's. That's it. Okay, so a polynomial function of degree n in the variable x means that the highest power of x is n. That's why it's an nth degree. And all these numbers, a sub n minus 1, a sub n minus 2, a sub 3, a sub 2, a sub 1, a sub 0, they are just coefficients. Okay, they're coefficients. They're just numbers. And the degree of the polynomial is the exponent of the highest power of x. That's it. Okay, so the graph of a polynomial function is both continuous and smooth. This is why we love polynomials. Polynomials are well-behaved curves. They are continuous, which means I can trace them without or draw them without ever picking up my pen or pencil. For instance, it's connected the whole way from beginning to end. Okay, discontinuous could be that we have a dot here and a jump down here. This is discontinuous. I have to pick up my pen in order to draw the complete graph. Now the fact that it's smooth and rounded, okay, there's no sharp corners. For instance, we want nothing like this sharp corner right there. No sharp turns, okay? No sharp turns. We don't like those. The last thing is to remember that the zero, or a root of a polynomial, is the value of x where the function f of x equals 0. That also means that y is 0. So the zero, or the root of a polynomial, is just the value of x when y is 0. Okay? Now we can classify polynomials two different ways. We can classify by degree, which we just said is the highest power of x. So a constant polynomial, the highest power of x is 0. So all that's going to be is a number. Okay, so an example would be y equals 5. That horizontal line, that's a constant function. Then we have a linear function. A linear function, remember, that's something like y equals mx plus b. That's x to the first. The highest power of x is 1. So it's a first degree polynomial. A quadratic is a second degree polynomial. It's going to have an x squared. It can have an x squared, an x, and a constant, but it doesn't have to have all three. It has to have an x squared. Now a cubic is a third degree. So it's going to have an x raised to the third. And a quartic is a fourth degree. That's x raised to the fourth. And a quintic would be a fifth degree polynomial. Anything higher than 5, for instance, if it's a sixth degree, we just call it a sixth degree polynomial, a 10th degree polynomial, a 12th degree polynomial. We're not going to worry about special names. Now, I am going to caution you about quadratic and quartic, okay? Because a lot of people will look at quad and they'll think about, oh, you know, a quad, when you go ride your quad, it's got 4 wheels. A quadratic is only a second degree. A quartic is your fourth degree. So watch out for those. Those are the two that people tend to confuse. Remember your quadratic formula. That was done with quadratic. So try to remember that way. Now, we can also classify polynomials by the number of terms that they have. Mono means 1. So a monomial has 1 term. So this example over here, y equals 5, not only is a constant, but it happens to be a monomial. Bi, like a bicycle, means 2. So this has 2 terms in a binomial. Tri, like a tricycle with 3 wheels, a trinomial has 3 terms. And poly means many. So a polynomial, we're going to use that for 4 or more terms in a polynomial. Now technically, all of these, monomial, binomial, trinomial, are all polynomials. They're just special cases of polynomials. So we talked about our classifying polynomials by degrees. These are pictures of the most basic of each of our first degree is linear, second degree is a parabola, our third degree, notice it hits the x-axis 3 times, a fourth degree hits the x-axis 4 times, and a fifth degree or a quintic. Now, will they always look like this? No. First degree always looks like a line, second degree always looks like a parabola. The others can vary a little bit, and we'll talk about that more as we get into the unit, okay? So the next thing I want to do is we're going to look at these 3 examples. We're going to find the degree for each of them. We're going to graph them on the Inspire, draw a quick sketch, and then we're going to look for a connection between the degree and the number of times the curve intersects the x-axis. So the first thing, if we look at the first problem, y equals x squared minus x minus 2, the highest power of x is 2. So this is a second degree polynomial, or a quadratic. This one, y equals x cubed plus 2x squared minus 5x minus 6, the highest power of x is 3. So that's a third degree polynomial, or a cubic. And then we have y equals x to the 4th plus 4x cubed minus x squared minus 16x minus 12. Our highest power of x is 4. That makes this a 4th degree polynomial, or a quartic. And now we're going to move over to our TI Inspires. We're going to graph them, and you're going to copy them onto paper. So we open a new document. I'm going to press Menu. I'm going to enter a graph page. I notice that the graph paper that I have has a different window, so I'm going to escape. I'm going to go to Menu, Window Zoom, Window Settings. My X-min is negative 10, so I can tab. My X-max is 10, so I can tab, but I'm counting by ones. Then I'm going to tab. My Y-min is negative 8, tab. And then my Y-max is 10, and we also counted by 1. Okay, so here we have all that. We click OK. Now our graph paper is the same size as the graph on the paper. We tab up. Our function is x squared minus x minus 2. Hit Enter. Now you can see what the graph looks like. Don't forget it has to have arrows. Hit Control T. Make sure you have some negative x's and some positive x's there. Plot your points, draw your graph. I'm going to add another page, and it's graphs. Again, I'm going to go to the menu, Window Zoom, Window Settings. My X-min and my X-max are both already set correctly for 10 and 10. I want to count by ones on my x-axis, and I'm going to tab. My y-mins this time go from negative 10, tab, to 8, tab, and we were counting by ones. So I'm going to tab and hit OK. This time my function is x raised to the 3rd, get out of your exponent, plus 2x squared minus 5x minus 6, and hit Enter. There's your graph. Don't forget the arrows. Hit Control T. You can see your points that you need to plot. So you want to plot those points and get a nice graph. Then I'm going to add a new page. You can pause this as you need to so that you can plot the points. Okay, pause as you need to. Control Dock, add a graph page. Again, I'm going to change the window zoom and the window settings. My x's are still from negative 10 to 10, and I'm counting by ones. However, my y-min is negative 30. My y-max is 10, tab, and I'm counting by 2s. So be careful because we're counting by 2s on the y-axis. Click OK. And then our function this time is x raised to the fourth, get out of your exponent, plus 4x raised to the third, get out of that exponent, minus x squared minus 16x minus 12. Hit enter. You can see what the graph looks like. It's going to have arrows. Control T to find your x values. Be careful when you plot it on paper. Remember the scale on the y-axis is 2. Pause now. Make sure you have all three graphs. Okay, so hopefully you have your sketches drawn. So now we want to look at the degree and the number of times the curve intersects the x-axis. So on this first example, it intersects the x-axis twice, and that's our degree. In the second example, it crosses the x-axis 1, 2, 3 times, and that's our degree. In the third example, it crosses the x-axis 1, 2, 3, 4 times, and that's the same as our degree. So we know that the degree equals the highest power of x, right? And it seems what we've just observed is that the number of times the curve intersected the x-axis was the same as the degree. And remember that the places where the graph crosses the x-axis are called the roots or the zeros. So we have this idea here that a polynomial of degree n has exactly n zeros. So in other words, if we have a third degree polynomial, we're going to have 3 roots or 3 zeros. If we have a fifth degree polynomial, 5 roots or 5 zeros. Now, does the number of zeros equal the number of x-intercepts? Well, it looked like it in all 3 examples that we did. And we could even look at an algebraic example here. F of x is x cubed minus x squared minus 2x. This is a cubic, right? A third degree. And if we factor out a common x, we'll have x squared minus x minus 2. And we could factor that again, right? That trinomial, we're going to need an x in the beginning of each. What multiplies to negative 2 and adds to negative 1? That would be a negative 2 and a positive 1. What would the roots be? What value of x makes x 0? That's x equals 0. What value of x makes x minus 2 0? That would be x equals 2. And what value of x makes x plus 1 0? That's x equals negative 1. So we have our 3 roots. 3 roots for a third degree polynomial. Also, by the way, if it's easier for you to set each factor equal to 0 and solve like you used to do with your t-charts, you're just going to have more than 2 columns, so it's not really a t anymore. That's absolutely fine, but I also would assume that the time you're at pre-calc, not all of you need to do that, and that's okay. All right, now we're still wondering, does the number of zeros equal the number of x-intercepts? So far, everything we've looked at says yes. Well, here are some exceptions. F of x is x cubed minus 6x squared plus 10x. So this is a third degree polynomial, right? So this is a third degree, which means we should have 3 roots or 3 zeros, but it only crosses the x-axis once. That's because we have 1 rational root, or real. We know it's real because it crosses the x-axis, which is real numbers. I happen to know it's rational because it's crossing at x equals 0. I also know I have 2 imaginary roots. How did I know that and you didn't? Well, that's something we're going to learn. We'll get to that, but I'll give you a little preview. If I was to move this x-axis up, do you see how it would here hit 3 times? Okay, so I know it has to have 3 roots, but only one of them is crossing the x-axis, so the other 2 must be imaginary. Well, let's take a look over here. This is a second degree quadratic, which means we should have 2 roots, right? But it's only touching the x-axis once here at negative 2. But we could look, because we're smart, we could look algebraically at f of x and say, all right, if I was to factor this, I'd need an x and an x, and what multiplies to 4 and adds to 4, that's positive 2 and positive 2. What do you notice? Those factors are the same, right? We're going to get the root x equals negative 2 and the root x equals negative 2. We're getting the same root twice. That's when we say we have one root of multiplicity 2, meaning we're getting the same answer twice. So, does the degree equal the number of x-intercepts? The answer is sometimes. When doesn't it happen? It does not happen if there are repeated roots or imaginary roots. Okay, and we're going to stop here for today. We're definitely going to go over more of this in class, so not to worry. You all have a wonderful day, and I'll see you soon. Bye, guys.